Hi everyone, this is Renee, and I thought I'd give another go at talking about the earthquake and moon phase correlation that I found almost by accident, not completely by accident, but nearly by accident. Um, a small but significant correlation was found, and I'd like to walk you through how I did it. There seems to be renewed vigor in astrological research or research with astronomy events as timings. And so I wanted to walk you through this in a perhaps more succinct way, a more awake way than what I posted this morning, which had a lot of diversions and digressions. And also I was pretty sleepy. So let's give this a shot again. All right. Here is a small write-up. You can find this write-up either in the link below or by going to my website, irastro.com, going down to media, articles, and then if you're watching this anytime in November of 2017, it'll just be here at the top. Or if it's later than November of 2017, go into the archives and choose November of 2017, and it will be in there. So, what happened? What did I do? Basically, first things first, I came across a Kaggle post, and let me show you Kaggle, and the post in particular. Kaggle, Kaggle, .com is a really fun site. It has a lot of data sets that people put up. It has a lot of discussion. Some programs are available for each data set that people submit. There's discussion on these kernels, as they're called, these small programs. And yeah, it's interesting. And there's some competitions, and you can kind of get your feet wet in data science in a safe way. The kernels are only really in Python or I think R are the two options for submitting a kernel. I looked at this data set and wanted to use my go-to program of Mathematica, and I wanted to use more data than was provided here. But this was certainly the catalyst for this whole study. So if you go to that page by clicking on this Kaggle post in the fourth paragraph, it'll take you to this page, and you'll see in the sort of subtitle it says, "Is there any relationship between earthquakes and solar system objects?" It's kind of a time-old question, isn't it? Is there any relationship between earthquakes and solar system objects? And for instance, I decided to look at this with regard to maybe the most fundamental astrology there is, which is looking at moon phases. And there's many ways to consider the moon and its phases. Shut off my phone. Including Tithi in Jyotish, right? Or nakshatra, certainly constellation. I decided to go, to start, this was just a start of a study. And I decided to start by considering the moon phases, just 8 of them. 8 of them. And the idea there is that there is more troublesome moon phases and less troublesome moon phases in Jyotish, right? If we're talking about Tithis, it's very interesting. There's dangerous, even in quotes, so-called dangerous kind of Tithis and very kind Tithis. This was not done with Tithis, but instead was done with moon phases. And the idea is that it's a very simple idea. You're someone from 10,000 years ago. you look up at the sky, you know at the very least that the difference between a new moon and a full moon. You know at the very least the difference between a new moon and the first quarter. You know the difference between the first quarter and waxing gibbous, waning gibbous, third quarter, waning crescent, and then back to new moon again. So with these 8 fundamental ways of splitting up the cycle, the lunar cycle, and also an inherent embedded notion, again from Vedic astrology, of, for instance, the new moon being the most troublemaking, the so-called malefic is a technical term, malefic, of the 8 stages. Full moon being the least malefic of the 8 stages. Okay, but what about the in-between stages? How malefic are they? Well, you can kind of figure that out by saying, okay, the waxing half, the Shukra Paksha of the moon, is kinder than the Shukra Paksha, than the Krishna Paksha, the dark half of the moon. So the waning half of the cycle. So with that said, if full moon is the kindest, the least malefic, if I want to set up a correlation to earthquake incidents, magnitude in particular of earthquake, maybe the hypothesis here is that maybe there's more, the stronger earthquakes during the new moon because it's the most malefic, and there's least amount of strength and magnitude of earthquake during the full moon because it's the kindest, least malefic influence, with again the intervening kind of stages having the in-between qualities. So we go from full moon as the least strong earthquakes in the hypothesis to waxing gibbous being the second in line, slightly more than full moon because it's slightly more towards the new moon, but it's on the waxing side, so it gets the next number of 2. The waning gibbous has the least, so the least kind, the most malefic of these 3, because it's in the waning half of the cycle. Similarly, first quarter is going to be more than these 3, with first quarter and third quarter being close, but third quarter being more malefic. So then we get 1, 2, 3, and then 4 for the first quarter, 5 for the third quarter, 6 for the waxing crescent, 7 for the waning crescent, 8 for the in this hypothesis the most strong of magnitude of earthquake happening. So it has the highest number, 8. So these are rankings. I know I used a number to annotate the rankings. That just means ranking number 1, ranking number 2, ranking number 3, ranking number 4, 5, 6, 7, 8. It doesn't mean that the new moon is going to be 8 times as strong in magnitude as the full moon. No, these are names. I could have called them Alfred, Bob, Charlie, David, etc. I could have just called them names, but the names I gave them describe the order. So 1, 2, 3, 4, 5, 6, 7, 8. These are nominal. These are names of rankings, and the order system being in that order from 1, 2, 3, 4, 5, 6, 7 to 8. I hope that's understandable. This is not a crazy idea. Uh, this kind of ranking system is used very commonly, actually, when things do not have an inherent quantitative value, but instead have a qualitative value, a relative qualitative value, then we can rank them. So if talking about the men's names that I gave, Alfred, Bob, Charlie, David, Eldritch, Fred, George, okay, 8 names for 8 men, and we rank them by height, that is perfectly fine to do so. And we could have just called them first in height, second in height, third in height, fourth in height, fifth in height, etc., sixth in height. But instead, we're calling them by their names. They have a name, a nominal qualitative property. It doesn't mean that George is going to be 7 times as tall as Alfred, just because he's number whatever that is, 7, versus Alfred being number 1. These are names, and I'm ranking these moon phases with respect to their names, or to their Jyotish qualities, to their qualitative aspects, not their quantitative aspects. And it's called a ranking system. So this is my ranking system. It's actually not even my ranking system. It's straight from Jyotish, like frankly Jyotish 101. Has this idea of the waxing half being nicer and better than the concomitant, like equal and opposite waning half of the lunar cycle, and the new moon being much more malefic in quality than the full moon, which has the kindest, the sweetest, most benefic notion attached to it, or quality attached to it. So this is the question. Is there any truth to this ranking system with respect to earthquake magnitude? So how do we get the earthquake magnitude data? You can go up here, and it describes how I got my earthquake magnitude data. Let's see. I got it from USGS, the United States Geological Service, and I specified between the window of January 1st, 1975 and January 1st, 2005 as the 30 years of my study. And those years were chosen because before first day of 1975, there was not a known uniform seismograph network like we have since January 1st of 1975. And you can read all about that in this really fascinating study, white paper published by the USGS that you can get by clicking on "A Uniform Seismograph Was Finally Used Throughout the World" link. And then, so that's a lower bound to the study, because before that, there wasn't a complete working network of seismographs, all of the same type, using the same units. So how can we go before that, is my thinking. And I used an upper bound of the first day of 2005. So why is that? Why did I do that? It's because hydraulic fracturing is known to cause some earthquakes. And if you click on this link about it was not yet in widespread practice, you open up an industry, a fracking industry website where they proudly describe how fracking is pretty much on an exponential increase. That's the light blue part of the graph. Since about 2005. Is pretty uniform. Maybe even 2000 is when the exponential growth really started to develop. Perhaps I should have used an upper bound of 2000. Maybe that's something one of you can do or I can do sometime. It's pretty simple. It takes about 2 seconds, in fact, to rerun this study using 2000 as an upper bound instead of 2005. Anyway, I use 2005 because of that graph. Okay, and here's a link from the USGS describing how fracking does come with some quakes associated with it. You can click on that link for more technical information, slightly more technical. All right, and so you get a bunch of data. Yeah, man. And you can download that data either directly from the USGS website, or I include it here for your own download from the article itself. Let's see what happens then. What's going to be in this spreadsheet is tons of data, longitude, latitude, time, date, magnitude, error and magnitude, depth, error and depth measurement, this kind of thing. I think there's like 40 columns to that spreadsheet. You only want 2 of them, okay? You only want the time date stamp and the magnitude. So we're going to toss all the other data out and just consider time date, which is in UTC, by the way, so Greenwich time, and magnitude. And the idea there is that we just build for each of those time date stamps what was the moon phase. And there's different ways of doing that. There's a military website. I probably should link to it. And I used an onboard astronomy feature in Mathematica to do mine. And you can get that digested spreadsheet down below in the article where it says, and please do confirm the results or perform your own test with the following digested.csv, which contains the date timestamps of the earthquakes all in UTC, followed for each by the moon phase ranking and then the magnitude. So this digested CSV only has 3 columns to it, right? And it has everything you need for this particular study. So what happens if we just correlate or establish a correlation function between moon phase ranking for an earthquake? What was the moon phase, which takes us to the moon phase ranking, right? Because there's a 1-to-1 relationship between moon phase and rank. So date timestamp takes us to moon phase, which takes us to rank. So that gives us a column of ranks, and then we have that column of magnitudes, earthquake magnitudes. So we have the rank for an earthquake and the magnitude for an earthquake. Is there what's called a monotonically increasing relationship between rank and earthquake magnitude? Which is to say, is it true that full moon has the least out of these moon phases of earthquake magnitudes? And is it true that new moon has the most? Is it true that waxing gibbous is slightly more than full moon, waning gibbous more than that, but less than first quarter, and so on? Is this assignment of rank truly correlative or in correlation to earthquake magnitude? It's a pretty straightforward question. So if you're following in terms of the science, the null hypothesis is that there is 0 correlation, nothing to do with correlation between that these moon phase ranks have nothing to do with earthquake magnitude. It's there's nothing there. The alternative hypothesis that I'm trying to test and see if it is true is that there is a non-zero correlation coefficient between ranks and magnitudes. So I had to use Spearman's row rank test for a couple of reasons. First, these rankings are not continuous. They go 1, 2, 3, 4, 5, etc. They're whole numbers. They're integers, in fact, and they don't have partial values. There's not like a rank 1.5, 1 3/4, 1 7/8, and so on. There's just these 8 ranks. That's all there is to it. That's something called a discrete ranking system. Is non-continuous. So we cannot use Pearson's for that reason, and also we cannot use Pearson's correlation coefficient because the magnitudes themselves are not normally distributed. Instead, there's a ton more of magnitude 5.5 than there is even of magnitude 6. And there's less of magnitude 6 as there is of magnitude 7. Less of magnitude 7 than... did I just say all of that in reverse? Okay, let me start over. I think I might have said it right, but let me start over. There's going to be a huge number of rank 5.5 earthquakes relative to rank 7 earthquakes or magnitude earthquakes relative to 9 magnitude earthquakes. There's only, in fact, in the 30 years of study, one magnitude of 9 earthquake, whereas there's thousands and thousands and thousands of the magnitude 5 earthquake. So type of earthquake. So for that reason, because there's this exponential relationship between number of earthquakes and magnitudes of earthquakes, I cannot use Pearson's for that reason either. Pearson's needs normally distributed data, as I understand it. So I had to use a different test, and it's perfectly appropriate. It's really good. It's called Spearman's row rank test, and you can Google that and get the equations. And there's a correlation row, as it's called, of 0.0252, which is a measure of effect size, and a p-value of 0.00325. So what does that mean? It means that there's this highly statistically significant event of correlation. However, the nature of that correlation is relatively weak compared to standards of considering effect size. I want to point out, though, that you have to take that with a huge grain of salt, because say you're in the industry of cancer prevention, and you have a medicine in front of you that has been shown to have an effect size of 0.0252, and it's a life-saving drug. You're going to be interested in that because 0.0252 for your industry is huge. So you have to consider industry when you consider effect size. You have to consider field of study, like biology versus geology. And I think the most important thing of all, you have to consider method of determining that effect size. So here it's a row rank test method. That's going to give you completely different kind of set of effect sizes than, say, Pearson's correlation coefficient, or compared to, say, ANOVA's, or compared to z-tests. You have to consider the field you're in, you have to consider the method of getting that effect size, and you have to consider the context. Like, are you saving people's lives? In which case, a 2.5% uptick is a good thing. a very good thing. Um, Here, we're in the field of geology, we're using Spearman's rho, and we're in the context of maybe someday far off in the future, being able to use this observation for maybe an earthquake prediction mechanism. It won't be the only component of that mechanism, but it's a component that will add 2.52% value to saving people from an earthquake, which is a good thing. Finally, even after you take all of that into account, you have to consider some other things too about effect size. So I want to just point your attention to this Abelson's paradox. I'll just read from the screen. You can, of course, read along too. I'll try to make it bigger for you. Abelson's paradox is an applied statistics paradox identified by Robert Abelson. This paradox pertains to a possible paradoxical relationship between the magnitude of an effect size and its meaning. So he gave an example from analyzing batting average in baseball and correlating that to skill level. So colloquially, batting average is considered among the most significant characteristics necessary for skill level in baseball. However, the effect size was only a tiny 0.003, about 1/10 of the effect size in the earthquake study. So I think, kind of hanging your hat on the idea of effect size is not reasonable. I'm not the only one to think that. Professor Cohen, who developed Cohen's D, considered like the prime example of effect size formula, cautioned strongly against people just saying, oh, something above 0.2 effect size is good and something below, or equal to 0.2 is bad, or any such framework like that is not reasonable. However, what do people do? They do exactly that because there's something digestible or easily graspable about the notion of effect size. The idea that you can compare it to different studies and see which one has is with regard to a stronger effect is compelling. However, you have to do it with great caution, and I think you have to do that here too. So an effect size using the Spearman's rank test came out to be 0.0252, and the p-value is 0.00325. So I think at the very least this is something compelling or worthy of future study as an anomaly, sort of a discovered almost by accident kind of anomaly in a history of earthquake studies, which we actually don't have that much data on. There's only 13,623 such earthquakes that fit within that 30-year band of January 1st, 1975 to January 1st, 2005, with magnitude greater than 5.5 and of any depth. That's not that much data, really. And yet, even with just that amount of data, the p-value is less than 0.05. And the correlation rho is not massive, but it's perhaps much like the batting average example, where batting average is one of many different characteristics for success in baseball, and hence a small effect size is not that worrisome. What you're more concerned about is p-value in these kinds of cases. So it might be here that just because the p-value, just because the effect size is rather small doesn't mean it's insignificant. And in fact, significance in this term or sense of statistical significance has it being extremely significant. So you can have a huge effect size but not be sure about it. That would be the case of a huge rho but a large p-value. You can have a small effect size and not be sure about it. That would be the case of a small rho and a large p-value. And and you can have the case here, which is a small rho, but also a very small p-value. So it's a small rho, but you're really pretty sure of it, and that's what's going on here. And of course, you can have a large rho and a small p-value, which would mean a large effect size and be very sure of it. That would be great, but that's not the case here. That's not what was found. If you're someone who wants sort of a visual, here you go. It's the one and only graph in the presentation, and it shows in yellow the 25th to 75th percentiles of the data in earthquake magnitude for each of the rankings 1 through 8. And you can see, for example, for the full moon with ranking 1, that there is the 25th percentile to 75th percentile shown in yellow. That whole block is low relative to the other rankings. And you can see how, for example, the new moon, which has the ranking of 8, has the 25th to 75th percentile higher than all the other ones. So go from the lowest for the new moon to the highest for the full moon, and the other stages being in between. If you're someone who really likes to just know the averages, what's the average of the earthquake magnitudes for rankings 1 through 8, you can look at the pink diamonds. And you can see, like in the middle, just take the middle value of the pink diamonds and you have a nice visual of a slowly but certainly increasing average as you go through the rankings. Something to consider with that set of pink diamonds is that you have to consider the height and the height of the diamond as well. That's going to show the 95% confidence interval. So the skinny diamonds are pretty confident that that's the mean. The thicker pink diamonds, there's less confidence of that middle mean value. So what you want to look for is non-overlapping diamonds from one rank to the next if you want to consider whether one rank has a different average of earthquake magnitude than another rank. Okay, so there's more to this plot than that, but you can Google box plot to get more information about how to read this. So, to conclude, a weak but highly statistically significant correlation was found between historic earthquake magnitudes and moon phase ranking. This is a fact. At this point, it's a fact. And again, I'm not sure how this particular study, even though it was done in like 2 hours, including the making of these pictures and maybe another hour for the write-up, I'm not sure how it could have been improved, because this is all the data we have between 1975 and 2005 of magnitude greater than 5.5 of any depth for earthquakes. And as to why I chose 5.5, it's considered what counts the start of what counts as serious earthquakes. So magnitude 5.5 and above is what's considered serious earthquake. So that's why I use 5.5. Yeah, I'm trying to think if I missed anything. The calculations are here. Um, yeah, free to download those, free to download the data. I look forward to your comments. Um, yeah, I've had a really good response to this. So I just wanted to put this up and out there, and let me know what you think with comments below. Bye.